this certainly is a very general question and has been treated for several decades now. So you may know about universal approximation results for two-forward networks and things like that were treated many years ago. So here we're going to be focusing on a very small class of networks which are relatively simple but have been gaining more and more popularity, especially in the world of machine learning, because of their simplicity, which allows people to use them efficiently. I'm going to present two examples for motivating the problems that we treat here in the introduction. Then I'm going to discuss the maximal information divergence and our approach, and then I'm going to conclude. So first example is I have here a recurrent neural network. This one is called restrictable machine. It has a full bipartite network, recurrent. There is one side which is assumed to be hidden and one side which is observed. Now, here this network can be used for many different things. In practice, people use this kind of networks for abstracting representations from data. And in this, it is important to get good parameter initializations for these networks by doing a unsupervised training phase. But one can just ask, so what happens if we present such a network with a whole bunch of data and try to maximize the likelihood of the data, and how well the activation probabilities that one observed in the visible units approximate the data depending on the number of hidden nodes of such a network. So at this little example, there is a database of handwritten digits, MDs. It's well known for people working in machine learning and consists of 60,000 28 by 28 bit digits, handwritten. And what one does is one fits this into this restrictable machine or some other network and try to tune the parameters such that when it runs by itself, like say keeps sampling fashion, then it will produce something. And here are some results for different numbers of hidden units. To the left, I have no hidden units. So that means that I have a number of, in this case, binary variables, which are all independent. What one can observe from the samples is that they are just giving the mean activation over all samples from the database. This one. What goes further to the right, I use their 10 hidden units, and then what sees a bit more of structure in the samples that one gets from this machine when it is running. And so with increasing number of hidden units, one can represent more structure. Now, leaving aside the question of how to train these machines over the question of the statistical approximation errors, and I'm just asking here how similar are the representations that I get or the samples that I get after training such machines when they have different sizes or different architectures. Now, this network has a very particular architecture because it's bipartite. But I'll give some more details later. Another example is slightly different in the sense that here, let me just explain the example first. So I have a robot here, which is something like an ant with 6 legs. This robot has sensors that it uses to perceive its environment. And it has actuators or some, let's say, variables that it can assign a value to. And this happens according to a probability distribution that is described here by a transition kernel, pi. So at a given moment in time, this robot has a sensory input, this ST, which is just the values of some sensors, a deviation of the legs, and a sensor which tells it whether it is touching the ground or something. And given these input values, there is going to be here a kernel that is going to cause the agent for this robot to choose an action from a probability distribution among the actions that it has available, like move the legs to the front or to the back. And this is going to be repeated. So this is a Markov process here. There's a Markov decision problem. And there is an idea of how to do unsupervised training for these agents such that they present interesting or coordinated behavior. And that is just take the joint distributions at a given time S, T, at a given time T and a given time the next time step T plus 1. This one is a joint quality distribution. And try to maximize the distance from this distribution to the distance of a distribution that consists of the marginals. That means maximize the mutual information of the sensory values at subsequent time steps. And this plugin factor reduces implicit behavior. Now you can ask how much structure can you put into such an agent? So how big can you make this mutual information? Obviously you don't necessarily have to take your product distributions and compare to those, but you could also take different kinds of theoretical structures and compare to these, how far you can get from there. And okay, we're going to take here a geometric approach, obviously. Very basic. We're going to be looking at finite sample space. Probability distributions there are just vectors with no negative entries adding up to 1. For 2 elementary events, this is a 1-dimensional simplex. For 3 elementary events, this is a 2-dimensional simplex like that. And we're going to be measuring distances in terms of the pullback divergence. Here's an example. If I plot the probability simplex for 4 elementary events, this is a tetrahedron. And if I plot the set of all probability distributions on 2 bits, or 4 elementary events, 4 strings of length 2 on a binary alphabet. And so all distributions of these 2 arguments which factorize like that can be plotted inside of this probability simplex, and this is just this saddle surface is a hyperbolic paraboloid or a product of lines if you want. And now if I take some point there in the probability simplex and I look at the distribution within the set of product probability distributions, the distributions we factorize like that, and they ask for the distribution that is closest to that given target, I find a point that is given by this formula. And I can ask so which target distribution I farthest. So there is here a 2-step thing going on. There is first a minimization with respect to the surface, and there is a maximization with respect to the entire probability simplex. So if I want to really find the points that are farthest away from being independent, then I have to do 2 things. So in this small example, I can just do it numerically, try to convince myself that these maximizers have a certain shape. And this has been treated theoretically also. So you can define an independence model just as a set of product functions that factorize on its arguments, on the arguments. You can think of this as the simplest neural network possible because it has units which are all observed and are all disconnected. And for this kind of models, there is a closed formula for the divergence, so it is known how to minimize this distance. This is just a difference of entropies. And there is a result for the maximal divergence. Say all the units or all the variables are curing, then if you compute the distance to that model, you will get something like this. One thing that I want to point out here is that when you start changing the cardinalities of the state spaces of the variables, then there are combinatorial problems that happen there. So if you want to find the maximal values of this distance, then you're going to be facing problems like answering whether there is a perfect code of a certain length and a certain minimum distance, which can be very hard. So therefore, well, in this talk especially, I will focus on two variables. Let's see, it can be anything like 2 to 3 or something, but all the units in the neighbors are kind of two. So to summarize here, this first step, observation here is that when the maximum Guido divergence to a certain set of probability distributions is zero, then you can say that that set of probability distributions is a universal approximator. In other words, there is no distribution on the probability simplex that it cannot approximate perfectly. And this is all the kind of questions that people have been looking at, historically for people-Werner networks and things like that. And now here, an observation. So we want to compute these two functions. When the set of distributions is an exponential family, say a neural network whose all units are observed, you just have a hierarchical model, and in principle you can compute what are the maximum likelihood estimators of such a model. So in expectation parameters, you would just take, compute the statistics of all the sufficient statistics at expectations, and this would give you a representation of the best approximation within a model. But this can be complicated because, well, for some reasons. But anyhow, this is much more easier than the case of neural networks because there are no unique projections, and it is not known how to maximize the likelihood of some data in a model. In fact, this is one of the big problems of neural networks, how to maximize the likelihood. There are some approaches, most of them are very beautiful, but later. So this is the topic of this work, to look into the approximation capabilities of statistical models defined by networks with hidden units. So these are the three ones that we're focusing on this work. First one is an naive-based model. That is a graphical model with a star graph. The inner node is hidden, and the leaf nodes are visible. This can be understood as a mixture model of product distributions, or in algebraic terms, this is a secant variety of a Sever variety, more or less. The restrictable machine is somewhat similar. This can be understood as a Hammer product of naive-based models, which means that for each probability distribution that you can represent with a naive-based model, you can multiply it with another one element-wise and renormalize, and this will give you a distribution from the restrictable machine model. And the deep belief network is something where you have a restrictable machine and then you sort of propagate all distributions that you can represent with that through a feed-forward network for several steps until you get an observation. It's a combined graphical model with undirected connections and directed connections. An example, just to visualize here a bit what is a bit different from exponential families. This is the naive-based model where I have three visible nodes, binary, and one hidden node, binary 2. This is sometimes called binary tripod tree model. And this is arguably one of the simplest neural networks with hidden units. What is interesting about this model is that if you count the number of parameters, it's equal to 7. Well, it's more than it's 7. And the dimension of this model is 7 too, so it is full dimensional. There are no parameters wasted. The ambient probability simplex is also of dimension 7, so it's full dimensional. However, it fits only a very small portion of that simplex. And describing that portion is hard, so there's no explicit description. In this particular case, there is one implicit description. If you want to tell which distributions lie inside of that model, there are inequality constraints, algebraic inequality constraints that you can formulate, in fact, for every naive-based model with a hidden variable which has 2 states. And in this particular case, you can do that too. However, even if you have this description and you're trying to find the best approximations at certain points, it's not necessarily easy. I am showing here, or I'm asking in this example, what is the best approximation of a certain distribution within that model? And I am depicting here, this is if you take the moments of the probability distributions which are within this model, and they have certain constraints that they must satisfy. And if I fix here the first moment, the first moments and the third moment to a certain value, and I plot the possible second moment information divergence to this kind of models, what we're going to do is we're going to identify families of exponential submodels of these neural network models, and then we're going to bound the divergence from the union of these submodels from above. So to illustrate the first part, or to illustrate this approach, let me say. So here again is the set of product distributions for 2 bits in blue. And a submodel, say this red curve, in this case that would be an IID model, 2 bits. And if I want to maximize the divergence to that model, I can, for example, try to test, the divergence from that model is certainly going to be larger than the divergence from the set of product distributions. But it may be, the way one can use submodels to understand the divergence from a larger model is that it may happen that if you have a collection of submodels and you look at the points that maximize the distance from these submodels, say in this case the red line, the maximizers of the distance from that model are here at the boundary, are this dashed line in red, like that. And for this green model, it would be this line, like going around. Now, the maximizers from the original model, the blue surface, they will be many times somewhere within the intersection of the maximizers of these 2 submodels. When that happens, then you can actually find the precise value of the maximum distance to the original model. Anyhow, and the kinds of submodels that we're going to be looking at here, that we looked at, are partition models. These are very simple exponential families. They are a special kind of convex exponential families, are actually just simplices within the probability simplex, are sets of probability distributions which have constant value on certain blocks of the set of elementary events. One can derive a closed formula for the divergence and maximal divergence of these models. An example is here. So 3 elementary events. Here, a partition model is shown with, which has this form. It's just a straight line going from the top vertex to the middle of the bottom line. And if you look at this shading, it's depicting the divergence from that model for each point. So, and well, clearly, these points here maximize the divergence to that model. The other kind of models that we're going to be looking at here as submodels for neural networks are mixtures of product distributions with disjoint supports. This is almost something like an naive-based model or a mixture of product distributions, but all the arguments of the mixture have disjoint supports, and this is crucial because when you do that, when you mix models with disjoint supports, if these models are exponential families, the result is going to be an exponential family as well. And for this particular class of exponential families, you can also more easily give a closed formula for the divergence and the maximal divergence. And they are similar to mixture models, which is something desirable if you want to look at hidden variables, which naturally cause some kinds of mixture to happen in this case of probability distribution. Now, neural networks can be analyzed in terms of these submodels. What we have to do is to show that they contain big such submodels, because if they are too small, we're going to get only like trivial bounds. And we have to find optimal projections into the unions of these models. And the problem is visualized here. If I have here a union of 3 straight lines, the distance to the union of these 3 lines behaves in a very strange way. So this causes a partition of the probability simplex. This is related to hypothesis testing. And we'll also talk perhaps that families of percentages where each of these models could represent a hypothesis, and depending on which hypothesis lies closer, assign an observation which would be a point in the simplex to either this hypothesis or that hypothesis. With the difference that's here, you have like entire continuous sets of distributions. Let me just present here the results briefly in a non-technical way. For this mixture of product distributions or naive-based model, we have this result. use the results for independence models when you assume that there is only one hidden state. Now in the case of replicable machines, the bound is slightly more complicated, but not much more. Here again, the maximum divergence to a set of distributions that can be represented by this neural network is bounded by this expression, and here the decay is the logarithm of the number of hidden variables times the q minus 1, that is the cardinality of the state space of each hidden variable, minus 1. This scales more or less with the number of parameters of the network for a fixed n. And this again subsumes results for naive-based models. Not in the version that is given here in the presentation in the slides, because here I am fixing the cardinality of the state space of the rules. In the general result of the paper is not. So when you have just one hidden node, then it's just an naive-based model. And now here for the deep elite network, here things are a bit more challenging because there's not only here a graphical probability model with hidden variables to be treated, but there's a concatenation of kernels that are applied to the distributions represented by this top model, restricted machine model, which is propagated somehow. Okay, here we obtain also bounds for the maximum distance to this model. And the decay is here on the nodes, given in the number of hidden layers. L is the number of layers of this stack. But here again, the cardinality of the state spaces of the units. We have a more general result for where the units don't have to take all the same number of states. Okay, here a qualitative illustration of these results. We have that the maximum model approximation errors of naive-based models, restricted open machines, and deep elite networks, they all increase at most logarithmically with the number of visible states. That is, when all the visible units have the same number of states, it increases with the number of units. And it decreases at least with the logarithm of the number of parameters, basically, so in a large scale. And this can be visualized like this. So if this is the logarithm of the number of parameters, and this is the number of observed variables, this would give a rough illustration of the bounds that we are providing here. Now, you see when this, on this side, when you have many more parameters than this, so it's exponential in the number of visible variables. These bounds become zero, and the models are universal approximators, meaning that they can basically represent any probability distribution in the state space. Now, the interesting thing is, we know that the moment when this happens is actually that big. So you cannot move this, you cannot improve these bounds to make that line go into that direction too much, because this almost, by counting parameters, you can conclude that you need to have enough parameters to be able to represent every distribution, so you can move that down. And the other part here, that the approximation error increases at least, or I mean, like in this way, when you don't have any hidden variables, that is a tight bound, which is because the bounds that we have for the independence models are tight, are actually equalities. So we have provided here this decay, so between these two lines, more or less. Now, obviously, computing the precise value of when this vanishes, this is very challenging, and this is something I'm personally very interested in. Continue working with this, but qualitatively, it won't change too much. I did here some empirical experiments, sort of validate these bounds to some extent. Now, for validating these results empirically, there are many difficulties, mainly because if you have a big neural network and you try for a given set of parameters to tell what probability distribution it is actually representing, that's very hard, because you have to normalize the distribution. And if you have many nodes, then that's an exponential there is no formula for telling what is the best approximation of a given target distribution. So you have to use some heuristics and a lot of parameter initializations and so forth. So therefore, I focus here on small networks. The top row is showing restricted Boltzmann machines with 3 and 4 visible binary units, and here the x-axis is showing an increase in the number of the units. The red line, the continuous red lines show the bounds on the maximal approximation error, and the blue lines show the empirical values that we found, the maximal values that we found for the divergence from the model. So what we did was we sampled actually millions of target distributions from Dirichlet private distribution, probability distributions with low entropy, say, so that they are concentrated on the boundaries of the probability simplex, and then for each one of these targets, we generated data, lots of data, and we trained the models using standard methods, contrasted divergence, and we also did maximum likelihood, gradient ascent with many parameter initializations, and then we became an approximation, and then we computed the divergence between these two points, the target and what we became for the network. So in gray you see like the distribution of the distances that we became for this target. One observation here is that you see that the red curve actually tells us that if you have your 2 units, the error shouldn't be larger than that. That's fine. Here for 3 units, the network should be actually a universal approximator. However, empirically, there still is an error. And that's because when the complexity of the network increases, the problem of actually computing or tuning the parameters such that it represents the target distributions that you are feeding it with is difficult. So it can happen that for some distributions, your algorithms just don't work that nice. So you get maximal distances which are actually bigger than the bounds. This shows, for example, that this has been discussed by some people recently, that some of these big networks are actually wasting capacity. So we are not actually